Welcome everyone to our second AirGradient Education Webinar. My name is Johanna and I will be your moderator for today. As you all know, our topic for today's webinar is how accurate is my air quality monitor? And I hope you're all in a great mood because today we're not only discussing about the webinar, but our CEO and founder, Ahim, will also be announcing the winners of our free monitor giveaway. So for those of you who submitted your stories and your interesting pictures, please stay tuned until the end of the webinar because you might be walking away with a free monitor from AirGradient. Great. Our speaker for today is Dr. Anika Cross. She's an expert in air pollution exposure science, data analysis, and management. In AirGradient, Anika coordinates a global project aimed at testing and improving our monitor. She ensures that research results and data are openly shared and creates educational materials to make air quality science more accessible to everyone, just like the webinar that we have today. We also encourage all of you here that joining to actively participate. So please use the chat box. If you have any questions throughout the presentation, you can leave it in the chat box and we will discuss it later through the dedicated Q&A sessions at the end. Also, before we start, I just want to inform that we are committed in respectful learning environment. So please find a brief of conduct shared into the chat box that outlines our expectations of your participation. Now let's give a warm welcome to our speaker for today, Dr. Anika. Hi, Anika. The stage is yours.
Thank you for the lovely introduction, Johanna. Okay, I'm going to share my screen. Okay. And as Johanna already mentioned, the topic of today is about the assessment of the sensing performance of air quality monitors. More specifically, we want to look at the accuracy and the precision. So just a little overview. I will first more generally talk about accuracy and precision and the concepts around that. I will then give you an idea of how you can determine it, like what experiments you would do to look at the sensor performance, and then how to quantify it. So there are certain parameters or errors you can calculate to quantify the accuracy and precision, and then also give you the tools to be able to interpret these parameters or these errors, like what is an acceptable error, what not. And all through the presentation, I will give you a few examples to make it clearer, to make it more understandable. Most of the data I will show you is basically, it's not real data, it's generated data by me to give you like crystal clear examples to understand the concepts better, but we will also have some real world examples in the end. All right, let's start with the precision and the accuracy. Some of you will probably already have seen this example with a dartboard, which is a quite intuitive example to understand precision and accuracy. So imagine you throw some darts, like 10 darts in a row at a dartboard, and you're always aiming for the middle. So this is our target value, basically. Then if you are a very accurate and precise thrower, then that's the ideal case. All of your darts would go exactly in the middle. If you're throwing very precisely, so you throw 10 darts in a row, you always hit exactly the same point. But if you're not so accurate, then this point might not be the correct point. But yet all of them are precisely going in the same direction or in the same position. If you're not so precise, but you're actually quite accurately throwing, then all of the darts will come close to the target value, but are a bit scattered around. So accuracy means that you're coming close to the true value, and precision just means that you're always hitting the same value, so it's repeatable. And then, of course, if you're neither accurate nor precise, then the darts would be all over the place. So what does that mean in the context of air quality measurements then? For this, let's do a little thought experiment. So let's imagine we have an air quality sensor in an airtight box, and we fill this box up with some particulate matter, PM2.5, until we have a known concentration of, let's say, 20 micrograms per cubic meter, for example. We close the box so that we have the stable concentration. If if we had this like sensors with these different characteristics, what would they measure? Again, in an ideal case, the sensor would just measure exactly the concentration that is in this box, 20 micrograms per cubic meter, and it wouldn't divert much from it. If we had a precise sensor, but it's not accurate, it would still measure all the time pretty much the same concentration. It's just not the correct concentration. If we have an accurate sensor, but it's not so precise, then all measurements would be around the correct value, the 20. However, they would be spread a bit more around it. And then if we have a sensor which is neither accurate nor precise, then yeah, the measurements have just nothing to do with the target value, basically. We can also look at that in form of a histogram. So if you focus here on the right top corner, you see a histogram. So that means the number of measurements for each value, which are measured. So again, the precise but not accurate sensor measured all the time around 10 micrograms per cubic meter, and 20 was the target. So the difference between the target and the ones that have the measurements that have been actually measured, this is an error, and this error can be used to describe the accuracy or to measure the accuracy of a sensor. So the average difference between what the sensor actually measures and what the sensor should measure, that gives you an idea about the accuracy of a sensor. And now we can also look at the second example here, where we have a low precision. So all of the measurements are around the correct value. However, the spread of the measurements, like the width of this histogram, is much bigger. So the width here gives us an idea about the precision. So that is the average distance from all of these measurements to the average value, which doesn't have to be the correct value, but in this case it is. That gives us an idea of the precision. So now that now we know the concepts of precision and accuracy, and we kind of know how to measure it, let's think about it in a more practical way. So how do we actually set up this experiment? I told you we need a box which is airtight. When we start with clean air, then we put a known number of particles on it, so that our aim in the end is we have a stable and known PM concentration. So the question is only, how do we get the air actually clean? Because pretty much everywhere in the world, you already have some particulate matter in the air, which you don't really exactly know the concentration of. So how do we do that? And then even more interesting, how do we find a known number of particulate matter, like a known number of particles or a mass? Like, do we buy it in a bag and then just blow it into the box? Or I don't know, is there like a gas cylinder where you can get a standard gas? So what I want to say with that is it's actually pretty complicated to realize a known concentration in an airtight box. More complicated than you would think in the first place, I guess. However, we could still say, well, but we can just close the box airtight, put the monitor in, and then we have at least a stable concentration. And with a stable concentration, we can still measure the precision, correct? That is correct. However, one big advantage of low-cost sensors is that you can have many of them. You can build networks. And if you want to check all of them with this experiment, then again, you need a lot of space. So for example, this picture here is our AirGradient test chamber, which is actually an entire room. And to make an entire room completely airtight is another story again. So it's actually also not really practicable. So generally, this chamber testing is not impossible, but not so common actually. A method which is much more common to look at the accuracy and precision of sensors is to collocate them with a reference instrument. So a reference instrument is basically the state of the art of modern science, of the best instrument we have to measure a specific pollutant. So in our case, let's say PM 2.5. And these reference instruments are big. They are regularly, they have to be calibrated regularly and maintained, and they're pretty expensive. But this is basically the golden standard which we have at the moment. And that is also what we're doing with AirGradient. So we have this big co-location project, where we put our outdoor sensors next to reference instruments all across the world. Here you can see an example from Chennai, and you can see the reference instrument is basically is much bigger than the outdoor sensors themselves, which I have zoomed in here a little bit. All right. So this is a practical thing. We co-locate it with a reference instrument. How do we get the accuracy then? So here you can see kind of an example of the measurements of the reference instrument, which we regard as a true value for now, and a random sensor in black. So remember, the accuracy was the average difference between the measurement and the true value, so between the measurement and the reference. So it's basically this difference here. And then the average difference, so that's across the whole time. So we can plot also a time plot of the difference for each measurement. And then the average difference should just be taking the average of this. So here we would have a mean error of 0.2 micrograms per cubic meter. That doesn't seem to reflect the difference we're seeing here. And the reason for that is that sometimes the sensor is below the reference and sometimes it's above the reference. So basically the negative and the positive references are canceling each other out. So that's why we need to take the absolute error. So absolute just means that all these negative differences are turned into positives, and then we take the mean error again, and now we get a mean absolute error of 9 micrograms per cubic meter, which reflects the reality much better. So yeah, that is already the first kind of quantity to measure the average error. It's called the mean absolute error. Here is the mathematical equation for it. Don't worry if you're not so familiar with these equations. It's just exactly what I told you. So it's the difference between the measurements of the sensor and the reference. These bars here just mean that you take the absolute value, so everything is positive. And then everything that has the ends in here just means that we're taking the average over all measurements of a specific time period. There's also another parameter, the root mean square error. So you see the equation here, but again, don't worry too much about it. It's very similar to the mean absolute error. So just instead of taking the absolute value, so these bars, we now take the square, because the square also makes everything positive. And then in the end, we have to compensate for the squaring by taking the square root. But yeah, don't worry if you're not familiar with these types of equations. Important is that it is also just a measure of the average error of a sensor. So it's it also describes the accuracy. And the RMSE is always higher or equal to the mean absolute error. So if you see an RMSE anywhere, then you can assume that this is the mean absolute error, or the mean absolute error is actually even smaller. And that makes it a little bit a stricter criterion, and that's also why it is recommended by the US Environmental Protection Agency. And that's also why we are usually looking at it. All right, so let's have a look at some examples of accuracy measurements. First of all, let's have a look at a good sensor and a bad sensor. So here you have two sensors and the measurements compared to a reference instrument. Which of these two sensors would you buy? And I assume that most of you would probably go for sensor 1 here on the left side, because the sensor just seems to be much closer to the true value, and that means that it's more accurate. And you would be, like, if you chose sensor 1, then you're right. This is the good sensor, so the more accurate sensor. And it's quite intuitive to see. And also when we look at the error down here, the error is much smaller. And this is also reflected in the mean absolute error, which is smaller than on the right side, and as well with the RMSE. So what we can conclude from here is the higher the error of the sensor, the lower the accuracy. So it's pretty intuitive, but now we can also, we know how to calculate the error and interpret it now. The second example is, again, two different sensors in different environments. So we have, I don't want to call it clean environment because obviously there is still pollution, but let's call it a less polluted environment and a more polluted environment. And again, which of these two sensors would you buy now? Most of you will probably go now for the right sensor because, again, that looks much closer to the reference value than the one in the less polluted environment. So let's look at the errors. But if we look at the errors, we can actually see that they have very similar errors. So does it mean that these two sensors also have the same performance? No, because we also need to consider the environment or the levels, the pollution levels where the sensor is in. So an error of 6 or 7 micrometers per cubic meter, micrograms per cubic meter, has a much larger impact on this environment where like the mean concentration is only 10 micrograms per cubic meter, and it has not such a big impact when the mean concentration is over 100 micrograms per cubic meter. And that's why we also have a normalized RMSE, which we look at. So that means just that we divide the RMSE by the average concentration. So you can see the calculation here. And then we find that this sensor here has a relative error of 66%. So on average, this sensor diverges or differs by 66% from the true value, whereas here it's only 6%, which makes it more accurate in a way. And yeah, this normalized RMSE or NRMSE helps us to compare sensors across different environments. And since we have lots of different environments in our collocation project, it's a pretty important parameter for us. All right, just a little summary of the accuracy so far. So it tells us how close a sensor measurement is to the true value. It can be determined by collocating the sensor with a reference instrument, and the accuracy is quantified by looking at the mean error between reference and sensor. So that could be the mean absolute error or the root mean square error. And then if you want to compare sensors in different environments, it's also important to normalize it. So let's come to the precision now. To remind you, the precision was the distance between of the measurements to the mean value. So basically the spread around the average value. So how do we do that when we compare the sensor and the reference instrument? So now we don't have a stable concentration anymore. So how do we see the spread? This is actually not really possible if we have like a constantly changing concentration. What we look at instead is the reproducibility of a sensor. So the reproducibility is the consistency of measurements across multiple low-cost sensors. Here's an example of that. So here we have 20 collocated AirGradient sensors, which are collocated here in our test chamber. And and you can see a timeline how they measure. And again, the precision was the spread of measurements around one constant concentration, but which we don't have here. But we do have, if we look at one point in time, we do have multiple measurements of sensors which are all exposed to the same concentration. So now we can look on the spread of measurements around the average value. So a spread around of different sensors around the average value. So maybe it's a bit clearer when I show it to you, like this is a zoom from our 3 o'clock. So here are all the 20 measurements of the different sensors. And now we can build an average value of these. And then the spread or the width of this spread, that tells us something about the reproducibility and also about the precision. So I just want to point out that the fact that we cannot measure directly the precision does not mean that we're losing information, because a reproducibility requires precision and consistency. So if the spread here gives us an information about how precise the sensors are and also how they compare across each other. So actually we're gaining information by doing this experiment instead of looking at a constant concentration. But back to our precision or reproducibility measurement. So we're looking at the spread here. How can we quantify it? For this, we're using the standard deviation. So this is a measure of the spread, or you could also call it the error across multiple sensors. And here we can see the formula for the standard deviation. Again, don't worry if you're not familiar with these terms. For the ones who are more interested in math, it's actually the same equation as for the RMSE, just that instead of the reference concentration here, we're now taking the mean value across all sensors. And also here, the lower the standard deviation, the smaller the spread here, and that means the higher is the precision of our sensors and the reproducibility. Also here, I want to give you an example of a less and the more polluted environment. So here we have two sensors, which in both environments, like in each environment, they have the same standard deviation of 1.5 micrograms per cubic meter. And again, here the spread looks much larger in this less polluted environment. And that is because the standard deviation has a much bigger impact when you're looking at lower concentrations. And just again, like with the accuracy, here we can also normalize the standard deviation. So again, by dividing it by the average concentration, we get a kind of normalized standard deviation, which is then called the coefficient of variation. So now we're getting into all the really fancy statistical terms, but as you can see, it's actually no magic. It's just divided by the mean concentration. And then you can see here that the relative spread basically is much larger here than in the more polluted environment. So the sensor here is actually pretty accurate, relatively seen. All right, so also let's do a quick recap about precision. It's about the spread of the measurements when you compare multiple sensors. So you collocate multiple sensors of the same kind with each other. You quantify it by the standard deviation, and you should also normalize it when you compare sensors across different environments. And when you normalize it, it's then called the coefficient of variation. So now that we have calculated, or we know how to calculate all these different parameters, the standard deviation, coefficient of variation, and so on, we also need to understand how to interpret these numbers. So what is an acceptable error? What is an acceptable standard deviation? And here the US Environmental Protection Agency has published some guidelines on how to test low-cost monitors, like air quality monitors, which basically most of our testing is also based on. And they have also given us some target values, basically, which in like some limits in which we should be with all of these errors, which I've just shown you. I want to add to this that there are also more aspects of sensing performance, which are also in these guidelines. For example, the linearity of measurements, R squared, and the bias. That's also very important to look at, but I cannot explain everything today. So we will cover that as well in the future with another webinar, or at least a blog article. But yeah, for now, we're just looking at the errors. And so an error of 30%, according to the EPA, is an acceptable error. Doesn't that seem a bit high that your sensor can like diverge by 30%? The reason why this is such a high number is that also reference instruments have their uncertainties. So I just took an example graph here of a comparison between two reference instruments, which I took from AQSpec, which is a website that tests air quality monitors. And yeah, as you can see here in this timeline, that there are also large differences sometimes between the two reference instruments. So also reference instruments have their uncertainty, and then if we compare our low-cost sensors with them, then the kind of allowed or acceptable uncertainty or error should be even a little bit higher than that to, you know, to make it rational. So this is also a quite interesting topic, and we're also planning to dive a bit more in detail into that later in another blog article or webinar. Okay, now I'll just come to two more real-world examples. I've already touched upon them, so I want to show you something like how to calculate the precision of our indoor monitors in our testing chamber. And then also I want to show you how to calculate the accuracy of our outdoor monitors in one of our co-locations, namely Chennai in India. So let's start with the precision. Here you can see like a timeline of 20 of these monitors here. And from this timeline, I can calculate the standard deviation and the coefficient of variation, so the normalized standard deviation. And on average, our monitors diverge from each other by about 11%. And both of these values actually are well within the EPA guidelines. So generally, we can say that the AirGradient PM sensors have are very precise and well within the limits recommended by the EPA. The second example is the accuracy of our monitors outdoors in Chennai. So here you can see a timeline of our AirGradient measurements in blue and the reference in red. Again, from that I can calculate the RMSE and the normalized RMSE. And you can see these values are relatively high and they're not in the EPA guidelines. However, I need to tell you as well that these are just the measurements as they come straight out of the plant tower modules without any calibration. And you can see that the measurements are still following the reference instruments quite closely. It's just that they're kind of systematically a bit too high. And if you look at a scatter plot, well, so this is a bit of a different topic and I don't have time to explain it in so much detail, but we have already touched upon it in some of our other webinars. So I put the links here and we'll share the presentation afterwards so you can look at that if you want to know more in detail about it. And we will probably also explain more about calibration and linearity in an extra contribution. Okay, but let's look at this just briefly. So the scatter plot can also tell us a bit about the quality of the measurements. The narrower these points build a line, so the more they build one line, and the larger, or like the closer our squared value is to 1, the better these measurements can kind of represent or follow the true values or the reference. And also the better you can improve the measurements with a calibration. So if we calibrate these values, you can see that now the measurements are actually pretty close to each other. And also the mean error in both absolute and relative terms decrease, and now they are in the EPA guidelines. So what we can conclude from this is that calibration improves the accuracy of sensors and the calibrated PM modules from the AirGradient monitors are within the EPA recommended limits. Right, this is my last slide, just to give you a very concise overview. So precision is about the consistency of measurements, and you can look at it if you compare different sensors of the same kind with each other. The performance parameters for the precision are the standard deviation and the coefficient of variation. Accuracy, however, looks at the agreement of the measurement with the true value. So how close is the measurement to the true value? Here you have to compare the sensors with the reference, and you're looking at RMSEs and MAAEs, so mean absolute errors. The EPA has given us some kind of recommendations or limits within our sensors should be. They are they are partially this kind of high because also reference instruments have their own uncertainty. And I showed you just now that by calibrating, you can sometimes improve the accuracy of sensors, and you can also improve the precision of sensors, sometimes by averaging them over time. However, this is both to a certain limit, like you cannot improve both of these things infinitely. Right, that was all from my side. Thanks you for your attention, and I'm happy to answer any questions.
Great. Thank you, Anika, for the presentation. I have seen so many questions on the chat box already. I think we can start with the first questions from Luciano. Based on the results of a co-location process, what are the steps to follow? Are fixes made to the monitors, example like OTA update?
Wait a second, I'll just have a look myself because I didn't acoustically get it.
Yeah, maybe I can say something.
No, I got it. Yes. But do you want to answer?
Yeah. So it's actually a discussion we just had recently that there could potentially be a lot of different correction algorithms that we develop, and we are planning to let the monitor primarily deliver the raw data and maybe implement some basic correction algorithms like for humidity, temperature in parallel to the raw data. And then we will publish the formulas that we develop so that people can then use them basically as post-processing. And it's just because there could potentially be a lot of different formulas, especially for PM, maybe based on climatic zones or, is it wildfire smoke or traffic smoke and so on. Yeah, I don't know, Annika, you want to add something then?
No, yeah, that's correct. Like depending on what the composition or like the material of the particulate matter is, we might need different calibration formulas, and that's why we would have several ones, which you then perhaps, I don't know, for example, choose on the dashboard which kind of particles you expect, and then hopefully you get the right calibration algorithm.
Okay, thank you, Aniha and Ahim. Luciano, I hope that answered your questions. And then moving on to the next questions from Christiana. What if you don't have the reference monitor?
Yeah, that's a good question. Well, you can always measure the precision, but obviously the accuracy is a bit more interesting. So you can measure the precision by not having a reference monitor and just placing several monitors together. If you don't have a reference monitor, yeah, well, basically you can't really tell the precision, at least for PM. As long you could also try to have the first experiment and create a known concentration. This way you could also know the accuracy. Another way would be to find a nearby monitoring station. This I know is not like evenly spread across the whole world. But many countries have reference stations, at least in bigger cities, and you can try to place the monitor close by. It doesn't have to be perfectly next to each other. You would also get an idea about the accuracy when they're like hundreds or maybe hundreds of meters or maybe even kilometers apart. You would still get an idea of the accuracy, but you cannot expect it to you know, agree 100% then anymore. Yeah, so that could be an idea to do then.
Okay, thank you, Anika. Next questions from Van Ilton. You have co-location projects around the world. How confident are you of the measurement when deploying a sensor in a country far from referencing projects such as Angola, where conditions are very different from the US, where your standards were adopted from?
Well, that is exactly the reason why we have so many different co-location places. So the calibration parameters, especially for PM, can vary a lot depending on the emission sources around and also on the meteorological conditions. So we're trying to have co-location, like so many different co-locations, so that we can capture all of these different conditions and hopefully are able then to get a better understanding of the impacts of different factors, for example, humidity, and also capture most kind of emission sources around. And then ideally, in the end, we can kind of make a very educated guess on like even countries where we don't have co-location places, but we can go to a similar country, for example, Ghana, or depending on the surrounding emission sources, just find kind of the closest co-location we have and then make an educated guess from there.
Thank you, Anika. I hope that answered your questions, Van Ilton. Next questions from Kwabena. Anika, in assessing and evaluating the accuracy of the sensor, do you ignore outliers? I'm asking this because some opinion has it that spikes observed in air quality monitoring must be ignored in some cases.
That's a very tricky question. Very good question, Corbina. Thank you for that. We're actually still discussing this a little bit, because on one side, you don't want to like exclude outliers because they might actually be true. Like you don't want to, it feels a bit like cheating if you exclude outliers from reference instruments. Sometimes they have outliers. But on the other hand, I think in the Environmental Protection Agency guidelines, they always speak of valid measurements. So, I mean, some outliers are obviously outliers, and these ones should be excluded. Like if you measure 5,000 micrograms per cubic meter or so, that is just not realistic. But it is very difficult to find, you know, an objective way to understand which is an obvious outlier and what might be an actual real measurement. So we're still in the process of defining that in an objective way for all of our co-locations. And if you have any input, then I'm really curious how you deal with this.
Okay, maybe moving on to our last questions here from Mudassir. Is the low-cost sensor only for ambient monitoring or for both, including an indoor environment? Do we have co-locations in India?
Yeah, so AirGradient has two types of sensors, one for indoor and one for outdoor. The PM sensors, which I just showed to you, are kind of the same. So we have the same modules in the indoor and the outdoor monitor. So you can kind of expect the same performance. And we do have co-locations in India. And the example I showed you about the co-location where I also calculated the accuracy, that was actually in Chennai in India.
Okay, I hope that answered your questions, Mudassir. Thank you so much, everybody, for asking, and thank you, Anika and Ahim, for helping with the questions. I think we can move on to we haven't get the closing yet, but we're moving on into our announcement for the free webinar giveaway. For your informations, we were absolutely blown away by all the incredible stories that you shared about how our monitors has been making an impact in your life. So without further ado, I'll invite our CEO and founder, Ahim, to share the winners with us. Ahim, the stage is yours.
Thank you, Johanna. Yeah, so basically, since we started deploying monitors all around the world, we hear feedback from people from everywhere, basically, in all kinds of lives and all kinds of situations. And we just got recently some really interesting stories about, for example, you might have heard that in northern Thailand, we had really bad air pollution, and we had this small preschool called the Mud House to manage their air quality better or monitor it better. And we got a really inspiring story from there. And this basically led us to want to know more how people use the monitors, how it helps them, basically. And we thought, hey, why not just ask the community, and to make it more worthwhile for you to share your stories. We said we will give away 6 monitors, and I will announce the winners in a second. We got, I think, primarily from 3 different types of people using it. So we had a couple of citizen scientists, just interesting to know what's going on, especially on the outdoor air quality. And also, like, we have the partnership with OpenAQ that they want to really contribute data from their location into a global data set to help science, basically, to understand air quality better. Then we also had a number of people concerned about, the health of their loved ones or of themselves. Some had like newborn babies, for example, wanting to know, hey, like, how healthy is the air quality in the kids' room? Do we need to improve something? And tied to that were also a number of people that wanted to understand specifically CO2 better. For example, having a home office in the basement, which is obviously not an ideal location because you might have a lack of ventilation, and so by measuring it, better understanding what's going on. So we had a really hard time choosing the 6 winners, and we actually planning to repeat that exercise. So even if you missed out this time, you have the chance to do it again. And here we are. So we have the 6 winners. I put the pictures here. My favorite one is actually the one on the right with the cute dolls there. And yeah, that's actually all I wanted to share. We're gonna email the winners in the next couple of days, and then the winners can choose if they want to have an indoor or an outdoor monitor. Yeah, Johanna, that's all from my side.
Great, thank you, Ahim, and congratulations to all the winner. I see the questions on the chat box. Probably Anika, do you mind to answer it? Our last questions. The question is, Anika, please, with your indoor monitors, have you conducted any comparative studies within mobile indoor microenvironment, for example, buses?
No, we haven't yet. We started with the indoor monitors needing Wi-Fi and also power. We're now in the process of making them also more independent by having mobile connection and running on solar power or maybe on batteries, but we haven't looked at mobile indoor environments yet. I do agree, though, that would be super interesting. In my previous work, I worked a lot in metro stations, and it's crazy to see the air pollution there. So that would be really interesting.
Wow, interesting. Thank you, Anika, for your answer. Okay, I think our time is almost up. So Anika, before we close it, could you please give a closing statement for the last time?
Yeah, sure. I'm actually really happy about this webinar and also that we had so many people. I was quite skeptic then on the Sunday and at this time we would have anyone. So I'm really happy that we had so many people watching. And also I'm really grateful for the questions that were all really good questions. And yeah, that just rounded it up to a really nice event. Thank you.
Thank you so much, Anika. I see that lots of you still wanted to ask some questions, but maybe we can reach out directly to us, to Anika or to Ahim. We will be very happy to answer some of your questions after this webinar. Okay, thank you so much, Anika, for the presentation. Thank you so much for Ahim for letting us know who the winner is. Let's give both of them a huge virtual round of applause here. And you can read the material for our webinar in article format within the link that you can find in the chat box. This basically summarizes the whole discussions for today. And as we promised before, we'll bring you more insightful information from science and beyond. So please keep an eye out on our future announcement in your email. So on behalf of the entire AirGradient team, thank you so much for joining our webinar. Have a great day, everyone.